introduce our last chair, Markus Elstner from Karlsruhe, and he's going to talk about multi-scale methods for electron and exciton transfer.
Okay, so thank you for the introduction, Jenny, and thank the organizers for putting together this very nice symposium and, of course, inviting me. So we are interested in electron and exciton transfer since quite some time, and we have been looking into a couple of different materials. We started with DNA, proteins, and now we are doing more and more also organic materials, disordered and ordered. And especially we also looked at break junction experiments, chemical injection of carriers and DNA, small, big molecules, and we were interested, is there a methodology which kind of, or can we compute the charge transfer, exciton transfer properties from like one methodology? And of course, the answer is no, but we were looking for something which was a little bit more general than things we found when we started. So nowadays, these efforts are very much funded by some DFG graduate schools, one about multi-scale methods in computational nanoscience, which is located in KIT Karlsruhe, another about fluorescence properties in biology, also located in KIT. And then we also involved in a research cooperative effort, an SFB in Heidelberg, which is very much about organic materials. So we have in that field some long-standing cooperations. So we collaborate with Jochen when we don't compete, and that's kind of on and off. So we have a cooperation, of course, with one of the core developers from DFDB, with Thomas Niehaus, and with machine learning guys, Anatol von Lilienfeld and Pascal Friedrich, which helped us to get going with this topic, and also with two colleagues from KIT and Heidelberg on exciton couplings. So when we started, of course, you can think of non-adiabatic dynamics, as Oleg has shown, and also using a semi-empirical method like DFDB or whatsoever. The systems we were interested in were way too large. On the other hand, it seemed that maybe 10 years back, you could quite get along very nicely with model Hamiltonian approaches. So people were using Landauer, for example, to compute conductance of molecules in break junctions, or you could go with Marcos theory. And at that time, the basic question was from where to get the tight binding parameters, electron-photon coupling, the bath, coupling to the bath. But I think that was then solved, or is nowadays really solved. And then it moved on to the observation, oh, these are kind of average parameters. What to do with thermodynamics here? And this problem of timescales, which has come up a couple of times. And we entered that actually first in biosystems, where a lot of work has been done by Beratan and Skurtis, but also a similar observation as we saw in Frank's talk, what Matyushov called non-ergodic kinetics. So the problem of determining lambda in a self-consistent way, because also in biology you have very slow modes which are maybe slower than the charge transfer rates. And on the right-hand side, organic materials, we have heard a lot. And so one solution was, oh, maybe we could propagate the wave function. And this is what we did, and I will talk about the methodology in a minute. And we applied this to DNA and photolysis, where you have a very, very fast charge transfer over 3 tryptophans, which couldn't be explained using Marcos theory. Okay, so what we were looking at is a theory which bridges kind of the ab initio type non-adiabatic dynamics and the model world, because the models are nice. We know what a coupling is, we know what a site energy is, we have an idea what reorganization energy is, and if we can kind of bridge this intuition with a propagation of the wave function, that would give us a lot of insight. And so what would we need for this? First of all, we have to chop the system, and then especially in biology, you need a QMMM coupling, because the fragments properties are very much dependent on what the environment does. In organic materials, that's less important. Then from whatever you compute for this fragment, throw away everything except like frontier orbitals and do this as fast as possible. That's where we use a semi-empirical method called DFTB. And also this comes from DFT. So DFTB inherits all the problems of DFT. So we also had to move to long-range corrected functionals. Now then you kind of do a superposition of the fragment orbitals and build your supramolecular wave function. And so this approach allows you to be very localized. So the charge or the exciton can be localized on one side, but it also can be delocalized over the whole system. And how do you know this? Yeah, you solve the time-dependent Schrödinger equation, which is coupled to the motion of the nuclei. And that's kind of the picture. You have the nuclei moving, and then that kind of kicks the charge or the exciton around in your system. This is just a slide on DFTB. I want to be very brief here. So we have the two options. We can use a PBE functional or long-range corrected functional. These are the two functionals which are available in the moment. DFTB is fast. It's like 3 orders of magnitude faster than DFT in a double zeta basis set. We are not talking about large basis sets. And what we get from DFT, we have these Hamilton matrix elements, H mu, which are pre-calculated. So we don't spend any time on matrix elements in the AO basis. And from that, we can compute the orbitals on the fragments. And then we put this together in 2008. We did that for DNA with the fragment orbital idea by Alessandro and Ferdinand Grossemer. They used that. And so basically, you do the solution for your fragment. It can be like an anthracene molecule out of the crystal. Then you get these MO coefficients, Ci, mu, nu, and then you plug in your pre-calculated minimal basis Hamiltonian and get this matrix H, which you can use then to compute Landauer currents, which we did, and which is a super bad idea for very big systems because we have all these problems with the time scale separation, which at least we couldn't solve at that time. Or you can, and that goes back to a paper Ferdinand Grossemer published before that, you just can plug this Hamiltonian, which you compute along a classical MD simulation and propagate the charge. Also, this didn't work in our hands because what you do is you have the atoms moving and then you kind of kick the charge around, but the back action of the charge on the nuclei is not in there. So we had to start from scratch and see how we can get these things in. So we started from the energy of an ionized system, n-1. And I don't go through all the formulas, but the basic idea is if you take the density of the ionized system and write it as a reference density of the neutral system and the charge density fluctuation, then you can reorder the terms and actually you come to an energy which is the energy of the neutral system minus the energy of the removed electron. And if you then want to go one order higher, you get some beyond Koopman approximation terms. We will not go to the second order term here. The 0 and first order are enough. Now, the point is this neutral energy we can substitute by force field energy because that's what force fields are parametrized for. You have your neutral system and that gives you all the motion there. And this matrix elements, if we expand it in our fragment orbital basis, we get this matrix elements. Now, this matrix elements you can compute from DFT, and if you do it with like GGA, actually no number is in there which is worth computing it. They're kind of all wrong, and that's what we have been struggling for a couple of years, how to get reliable estimates of T and epsilon. The epsilons are the Kohn-Sham levels of the different sites. So if you have like anthracene, all the site energies are the same. And it's not a problem if your HOMO levels are kind of 2, 3 eV off. But if you have two different molecules, then the difference in the epsilons makes a big makes a big error. The t I will come to in a minute. Okay. Now, if you compute this Hamiltonian and long MD simulation, you see that the side energies fluctuate, the couplings fluctuate, but most importantly, and that was Frank has been talking about, is that if a charge moves from one side to the next, the energy of this side just goes down. And that's what you see on the left lower graph. You get a very large reorganization energy, which is mostly outer sphere if you're in biology, and you have a lot of water reorganization. And this is what in our simulations we get through a QMMM coupling term. So we have a charge and the waters rearrange according to what the charge is. And then, of course, you have the inner sphere, and this is by lambda. And the important thing is here that you effectively can model the change of the side energy with this reorganization energy times delta QM, the charge which is on this side. Now coming to the time scales. So if you put a charge on one of the molecules, the side energy will go down. And then it's a big question, what are the time scales? And that's what Frank, I think, was talking about in quite some length. And we, of course, have the same issue because when we look to the same type of molecules. And in biology, as I said, in this cryptochromes and photolysis, it's actually a similar issue. When it's the hole is delocalized, then actually this lowering of the side energy distributes over several sites, and actually the effect of lambda becomes small. I show you in a couple of slides. Okay, now in 2010, then you have the energy, which is just in the top. You just take derivatives of that, or what we did, we took a Lagrangian and then from that computed the coupled equation of motions. So you have this A dots, which are just the expansion coefficients of the MO basis. And then you have the equations for the classic nuclei, which you can write as the derivatives of the force field energy and this delta F. And in charge transfer or exciton transfer, ET I call it here, this is the difference of the forces between the charged and uncharged sites. It's actually easy to compute, but there are several ways to implement that. So Jochen's group is doing that differently than we, but basically we have the same problem. But this delta F, so what happens is you put a charge on the side, the side changes its geometry, and as effect, the side energy lowers. This is what you also can put on the Hamiltonian and remove it from the classical Newton equations. So if we have the classical forces, then that's what we call explicit. But if we move it to the Hamiltonian and run the molecular dynamics on the classical surface, that's what we call implicit. And I will talk about that in some time. Okay, how are the DFDB couplings? That's where we had a collaboration with Jochen. So Adam and Jochen, they constructed all the reference data. And if you compare the DFTB couplings, you see these blue triangles. They are roughly 1.5, a factor of 1.5 off. This is consistent for all the data we looked at. So we came to the idea, why don't we just scale all this? And so for DFTB, you need a scaling factor of 1.5, and then you get couplings which are pretty accurate. And up to now, that seemed to hold for the systems we looked at. Now, Jochen and Adam are compiling a bigger data set. Let's see what happens there. Excitons, we have two options. We go to time-dependent DFT, solve the Casita equation, get something what we call transition charges. And with these transition charges, we can compute the Coulomb couplings, or we can compute supermolecular couplings. So you compute a dimer, and from the splittings of the dimer, you get these couplings. And this is, first we applied it to bacterial chlorophylls and LH2. And actually, when we use a range-separated DFT, we get really pretty much the same results as full-blown range-separated DFT. And again, GGA doesn't really work here. Same story for couplings and organic molecules. This is just a paper which came out and collaboration with Sebastian Höfner and Andreas Doy. LC-DFTB most of the time is really more or less in line with shows the same errors as omega B97X, which we used here for comparison. Okay, in the next talk, I will talk about CT states, maybe next year, but due to time, I leave this out. Short note on reorganization energies. So there's this paper from the Engels group, which actually says reference is equation of motion coupled cluster, so high-level quantum chemistry. And they say if you use, again, long-range corrected omega B97X, you have an error of less than 10%. If you use B3-lip, error is 20 to 30%. If you use PBE, like the standard DFTB, you have an error of 50%. And the reorganization energy is the real critical thing for the mobility here. So same thing, this is a paper we just published on excitation energies with LC-DFTB. So for exciton transfer, we also have to compute the reorganization energies. When we use LC, we are pretty much in line with CAM B3-lip, but if we use PBE, we are way off. Okay, now we wind back 5-6 years. At that time, we only had the DFTB GGA type simulations, and we did Ehrenfest simulations. That means we just propagated, as Vitao asked on Monday, can you just take this Hamiltonian and propagate the wave function and couple this to the motions? And yes, that's what we did. And you kind of compute the diffusion constant, and from that the mobility and that along 1D. So we take 1D systems out of there. And the surprise was, so this is GGA, reorganization energies, Ehrenfest dynamics, and we were pretty much on the experimental mobilities, and also the value of n, which we fitted from our data, was pretty good, except for the C direction, which is quite complicated, in line with experiment. Okay, we did some more systems here, but I will. So then Weiwei had a deeper look, because that was Ehrenfest, and then he kind of picked up a surface hopping implementation we did some years ago. And if you look at these red squares, this is SC, FF, FSSH, ST, RD. So these are all the corrections to surface hopping, which Antoine Karoff was talking on Monday. So we also have them. And what we did here, we took the anthracene MD, and these V equal 41 milli EV, this is just the dynamics we do with the normal anthracene. And the 13 MeV and the 3 milli EV, there we just scaled the couplings uniformly to get, like, with the same reorganization energy for anthracene, we get smaller couplings, and we were interested in the different regimes. And we found we can go really from hopping to this delocalized drift mode. And you also see on the right-hand side, so for the small coupling regime, you have really the charge, the IPR is the charge on the side. It's localized to one side, then it goes to two sides, and for the genuine anthracene parameters, we are between 2 and 2.5 sides. Okay, now I had this question, why is Marcus equation, when we use it so often, this is from Simone Frantini's paper, 2016, they say, okay, and also Frank indicated that they also always see Marcus equation quite far off. When we do it, we always see it on spot. I show you a very frightening slide in 2 minutes. Okay, now we go and use this implicit dynamics, because then we can play with the lambda. And first of all, how does implicit dynamics compare with explicit? This is what this graph shows. The implicit overestimates by maximum a factor of 2. So these broken lines are 1/2 or twice the mobilities. So this is kind of the accuracy check. So if we go from explicit to implicit dynamics which is very simple, and that gives you the back reaction actually. Although you go on the surface with the force field of the neutral molecules. Okay. And now we play with the lambdas. You see here for these materials we looked at, lambda DFTB is basically PBE lambda, B3 lip lambda, omega B97 lambda. If we trust the Engels group, that's the right value. And the difference is dramatic. And now if we go to the mobilities, we see on the left side GGA PBE overestimates, B3 lip is actually very on the spot, and LC-DFT underestimates, especially those materials with mobilities below 1. Now, why is that? Mobility is lower with larger lambda, that's clear. And it seems to be not so important for high mobilities. And that's what I already mentioned. If you look to the IPR on the upper left, so the charge is very much localized onto 1 or 2 sides if you have mobilities up to 1. If you go around 10, you have a delocalization over 5 sides. Then this lambda actually doesn't matter anymore. And that partially explains why our data was quite good already in our 2015 paper. You have, for anthracene, you have already decent delocalization. Okay, now, why is B3 lip so good all over? For proton transfer reactions, we know B3 lip, for example, underestimates the barriers typically by 3 kcal. 0-point vibrational energies are 3 kcal. So it looks like B3 lip is the wonder method which implicitly incorporates CPEs. This is to provoke some questions. Okay, this is the comparison with Jochen's paper. We have few outliers where we get a little bit different couplings, but otherwise it's nice to see that different simulations who have very different approaches, but basically do the same, but kind of do the same in different ways, gives you very similar data. So we were amazed to see this. We have here the propagation where we don't do the full propagation, but so we expect to be a little bit higher. And okay, if there are questions, I'm happy to talk about this. And this is, that's just data Weiwei sent me this morning. And the upper graph is about Marcus theory. The lower is transient localization theory. And for me, this Marcus theory is for 300K and B3 lip reorganization energies, it's just on spot. And that's what you see very often. I mean, it's really wrong for all other temperatures, and but here it's okay. Now, one application. So a colleague in Karlsruhe, they do a lot of MOFs, and they used pentacene. Organic chemistry colleague made the linkers for the pentacene. And the idea was, pentacene has a mobility of like 5 or 6, if I remember right. If we kind of anchor these molecules in a way that maybe the distance is decreased, can we create, based on MOFs, materials where we can invoke higher mobilities? So this trial was not very successful. They found a much lower mobility. And then they were asking why. And I mean, the answer is in the picture on the upper right. The two, so it's just that the fluctuations are much larger. And this is what you see in the table. The average couplings are 30 millieV, 36 for the pentacene crystal. It's not so big, but the big difference, but the fluctuations are much larger. And indeed, what we see, that's the graph in the middle, we see a temperature dependence, which points towards hopping. And experiment says it's a 64 millieV activation barrier. And we see that also in this MOF-based pentacene, we have a delocalization over 2.2 sites on average. In pentacene, it's 2.6. And this kind of explains the difference. For these simulations, we use the B3 lip reorganization energies with the implicit. Okay. Now, just briefly, I have 2-3 slides on that. So DFTB is within this FO thing is quite fast, and it seems that we can, with a good accuracy, model the mobilities. But this is all in 1D. And maybe we want to also put the relaxation into place in a little bit better way than implicit. And the question is, can we learn this? And what we first did was, okay, we used kernel-rich regression, and to represent, we used the Coulomb matrix. And if you look at the CT is charge transfer, ET is exciton transfer. So we learned the exciton couplings, the charge transfer couplings, and actually to get accuracy less than 10 to the minus 3, we had to go to 20,000 examples, 25,000. You see here the scatter plots. And now it's a little bit difficult from the scatter plots to judge, oh, is this good enough or do we need more? So this is for exciton couplings. And but when we looked to the performance for the regression, this is what you see in this table. Actually, when you have in a training set of 100,000 or 1,000, it's not faster than DFTB. So to code the information which DFTB as an analytical type simulation method has, you have to pay the same price. It's actually very different for exciton transfer, because there we have to do TD-DFT, and so that really pays off from the beginning. You know? So then the question is, what accuracy do we need? And then we did again with these Hamiltonians the simulations, and we found actually with training data 1,000 conformations seems to give us mobilities in the right regime. So now we moved over to neural networks, because exactly of this formula here, if we want to make a prediction, we have to run over the whole training set, and that scaling is a little bit better in neural networks. And then with the neural networks, we can also learn the NUC-Vs, maybe in one network. The first results we have say that actually we now are maybe up to a factor 10 faster than DFTB. And with this, I thank you for your attention. Hello?
Thank you. Thank you very much. Marcus, you finished?
Yes, I'm finished.
Yeah. So thanks very much indeed. I've got a couple of questions for you. I'm sorry, my camera is still blocked, so I can't turn it on, okay. But I am here. And the first question comes from Frank Orkman. Thanks for the nice talk. In the case of the pentacene-based MOF that you talked about towards the end, what was the transport direction? Did you see any anisotropy in that system?
Oh, yeah, we just took one direction. Yeah, so that's
which direction?
Oh, I would have to look it up. I don't know. Maybe Farad, if he's there, he can post it.
Okay, he can write an answer to
yeah,
the
he's the
question.
responsible guy for this thing.
Okay, job for Farad. Thank you. And next question is from Weitao, and he's asking you, how do you determine the charge of your fragments? For example, do you get fractional charges, and what do you do for the energy and force with fractional charges?
Yeah, I mean, yes, we get absolutely fractional charges. And this is, if you look here, for example, Ehrenfest, this is just the squared of the AN. That is the population on the side.
Mm-hmm.
And if you look to this delta E here, I mean, this is actually what we really use. And that's what we see, that the charge, then the whole wave function squared is, but that doesn't affect so what we do then in the delta F, for example, if we make it explicit, we weight the forces on the sides with this fraction of charge.
Okay. Thank you. I've still got a couple more questions come in, all in the last 20 seconds. I think this one, I think it's from Felix. Is there an easy way to understand why the DFTB couplings are too small? Is it just because the basis functions are not diffuse enough, or for some other reason?
I mean, there are two things. No, one is really a GGA problem. So if you look, so if we now talk about the charge transfer couplings, you see the green things are, I don't know, Jochen, maybe you jump in, or Adam, it's the green are FODFT, maybe it's something like B-lip or so.
Mm-hmm.
And we have PBE. So this is really a PBE problem. Yeah.
Okay.
And the same then for, yeah, I mean, you see that all over. It's a GGA problem. The couplings and for excitons and for, actually, if I go back here, you see how much this is the, so Jochen and Adam did CDFT. 0 means 0% Hartree-Fock. CDFT 50 means 50% Hartree-Fock. That's just on spot, the red guys. So it's really very much dependent on the amount of Hartree-Fock you have in there.
Okay, then I think this is the last question. I think it's from Sergey. Marcus, a great presentation. Are you gauging your ML coupling versus the expected Coulomb scaling of couplings with distance in CT and ET? He's a bit worried about non-spatial locality, which might affect the results. Does that?
I think I don't understand.
Okay.
So, I mean, what we just do here is a regression model. Maybe we discuss.
Are you checking for the Coulombic, the expected scaling with distance that you'd expect for Coulombic interactions? I think.
Yeah, I mean, we since we have a training set of, let's say, 30,000 dimers, this is the distance and the torsional dependence is kind of fitted in. Yeah. And yeah, what we use is the Coulomb matrix. That's true. I mean, it doesn't have the inbuilt, I mean, one could use an exponential scaling. Maybe that is better. We didn't try this. I don't know whether that was the question. Yeah, so the Coulomb matrix goes, of course, 1 over R. The couplings, exciton, the charge transfer couplings go exponential. Maybe a better representation would learn better, but maybe I missed the question.
Okay, well, the question is in the chat, so you can have a look at it and see if you understand it better when reading it. And I think that brings us to the end of the question. So I'd like to thank you very much for the presentation. And we're going to move on now to a series of lightning talks.